Hello, hello, hello. So, I'm at UNSW today, and I thought I'd record a video explaining further trig integrals. Um, Particularly, I'll be dealing with it in terms of families. I think a lot of these aren't given on your reference sheet, so I want to kind of be able to draw some comparisons to the ones that are given on your reference sheet so that you can easily be able to integrate particular functions in the extension 1 exams. Okay, so there are a few things you need to know. First, with maths, there's a lot of incest. Okay. What I mean is these trig functions, they like to keep it in the family. Okay. They right? So they like to sort of stick together and they keep it in the family, um, particularly with the derivatives and with the integrals as well. So I'll show you what I mean. Now, at least this is the way that I sort of reasoned it when I was in year 12, and it sort of made sense to me. And that's kind of how I think about it now as well. The idea is that you have this first family, which is sine, tan, and sec. We have a lot of relationships between sine, tan, and sec. Okay. Particularly the derivative of tan is sec squared. The derivative of sec is sec x tan x. We also have our property 1 plus tan squared x equals sec squared x. What I'm trying to say is these ones, they like to sort of they hang around each other all the time. They show up in the same formulas and the same identities. Okay. I mean, you already know that if you take the derivative of 10x, you get sec squared x. Okay. I want you to just have a go at differentiating sec x yourself. I think write it as 1 on cos and then do chain rule. And you end up getting sec x 10x. So you can see how, right, taking the derivative of 10 keeps it in the family, right? It's still sec squared. Take the derivative of sec, you keep it in the family. It's sec x 10x. Okay? That's the idea that I'm trying to present here. The second family is cos, cot, and cosec. Now, even though you might be given this in the reference sheet, you might be able to quickly derive that. And I guess you're not really given this in the reference sheet, but it's one thing that you got to keep in mind. You're not really given much information about these ones. Okay, particularly you're not given the derivative of cot x, and you're not given the derivative of cosec x either. But I want you to just sort of look at the first family and look at the second family and look at sort of the corresponding members of those families, right? I feel like we can all say sine x sort of corresponds with the cos x. They're like the two OG functions, okay? Tan x, that's given as sine on cos, and then cot's the reciprocal of that. So they're sort of related. I don't want to say related, they're two separate families. They're sort of connected in a way. And then we have sec being the reciprocal function, and then cosec being a reciprocal function. So particularly reciprocals of the sines and the coses, those two sort of have a connection as well. Nice. We know one property with this second family is 1 plus cot squared x equals cosec squared. Okay. And we also know that if we take the derivative of cot x, you can do it yourself. You can do it by taking 1 on 10, by writing it as 1 on 10, and then doing chain rule. I mean, you can have a go if you'd like. But what we get is negative cosec squared. Now, how are you going to remember this in the exam? Well, the way that I would remember it is I'd say, well, if the derivative of 10 kept it in the family and it gave you sec squared, then if you take the derivative of cot, it's going to keep it in the family. But see how this is sec? It's going to get its respective version from that family, which is cosec. I'll talk about the negative in a moment. Another one, if you take the derivative of cosec x, just look at what you have here. The derivative of sec was itself and was the tan function. So if we're trying to sort of suggest or predict what the derivative of cosec is going to be, it sort of makes sense to say, well, it's going to be itself and then its version of tan, which is cot. I don't know if this is making sense to you at all, but this is just sort of how I remembered it. Okay, you can, if you want, come up with your own way, but I think this whole family incest method sort of makes sense, unfortunately. Now, what sort of extra property does family 2 have? Well, family 2, if you differentiate any of these functions, you can even think of it as another way. Instead of thinking of it as this family, you can think of it as the functions that start with C. So start with C. Okay. The derivative will be negative. Which is why the derivative of cos is minus sine. That's why the derivative of cot is minus cosec squared. And that's why the derivative of cosec is minus cosec cot. Okay. I think if you can come up with some way to figure these ones out or to be able to remember these, then it's going to save you a lot of time instead of having to go and differentiate them off to the side to prove what you need to, I guess, prove in the exam. Well, not even to prove what you need to prove in the exam, because sometimes they'll just ask you, what's the integral of sec x tan x? And you have to know that that's just sec x. Okay. I know it sucks, but with more practice, it sort of makes sense. And I think we already know that the integral of sec squared gives you tan x plus c. Okay. You kind of have to be able to recall these automatically. On the respective family 2 side, if you have the integral of, let's do cosec x cot x, because you know the derivative of cosec gives you minus cosec cot. So if you're going to integrate cosec cot, this should give you minus cosec x. Okay. And similarly, if you have the integral of, what's the other one? Cosec squared, my bad. Because you know the derivative of cot is minus cosec squared, if you're going to integrate cosec squared, it should give you minus cot. Then plus c. Perfect. Now, even though there's a lot of incest going on between these families, in that they're trying to keep it all amongst themselves, there are these two philanderers who sort of, I don't know, they kind of cross families, okay? Particularly if you have the integral of tan x and you have the integral of cot x. The integral of tan x, remember we'll write it as sine on cos. The derivative of cos is minus sine, so let me put a negative there and put a negative there. And now it looks like the derivative over the original, so it's going to be a log function, so minus ln of the absolute of cos x plus c. So you can see they didn't really keep it in the family here, because if you integrate tan, it doesn't just give you sines, secs, and tans. It actually gives you a cos. So this is one of those ones where my little model falls apart. But we can not consider it as falling apart. We can consider it as, there's always like the odd one out in every family. In a family filled with incest, there's got to be one who's, not attracted to their family members. Oh, I can't believe I'm saying this. Okay. And for cot x, similarly, we're going to write this as cos x on sine x dx. And then the derivative of sine is just cos. So this is just going to be equal to ln of the absolute of sine x plus c. Okay. Not bad. These are the main sort of integrals that you need to know. These 6 that I've given you down here. Okay, of course, you already know the integral of like sine and cos, so we're not going to deal with that one or deal with writing those ones. But these are the main 6 that you have to be able to ensure you can recall. Okay, and just as a point of, I guess, clarity, they also work for chain rule, right? So what that means is if you have the integral of cosec squared 2x, part of the chain rule is to say, yeah, okay, this goes to tan. Sorry, this goes to negative cot, my bad, of 2x, but I have to divide by the derivative of the inside. Okay? So just keep that in mind. Another point to make as well, let's say you had sec 2x tan x. You can't use any of these 6 to integrate this, at least not directly. The reason is because, of course, you have different arguments. They need to be of the same argument. If this was a 2, then that's fine. You would just do, oh, this would go to sec, but you got to divide by the inside, so the derivative of the inside, so it'd be 1 on 2 sec of 2x. But because you don't have the 2 there, maybe you have to expand the sec 2x to get it into compound, like using your double angle expansion. Who knows? It might come out nice. Maybe you have to, I don't know, work at it a bit more. Okay. So those are some important points to make. Let's just put that as a note. Nice. So I'm going to deal with a few different types of trig integrals. So I've sort of given you a bit of a rundown. Oops, it's laggy. No, it's all good. So I've sort of given you a bit of a rundown. These are things that you're going to have to know. But now I'm going to show you how to integrate other trig integrals which aren't directly obvious. Okay. So let's write integration of sine squared x and cos squared x. Okay. Integrating sine squared x. You might say this is reverse chain rule. And you'll look and you'll recognize that, oh, the reverse chain rule formula still tells you, so chain rule, sack writing that out, tells you if you have f dash x times some function put to a higher power, when you integrate it, you'll be dividing by the derivative of the function, because that's the inside, and you'll be canceling off the f dash x, so you're not introducing new x's, which is good. And you'll just be effectively adding 1 to the power and then dividing by the new power. Okay? And then plus 6, of course. That's not the case here. Because if you consider this to be, maybe we write it in a bit of a different form. We write it as sine x squared. This becomes like the f of x. But you need the f dash x present on the outside. You need that derivative of sine, which is cos. You don't have a cos x on the outside, so we can't do reverse chain rule. And nor can we just go and divide by the derivative of the inside. So divide by the cos x, because that's going to be, we're going to be introducing new x's as we apply the integral. And we're not allowed to do that. Okay. So what's the method? Well, the method is to use our double angle expansions. Particularly, this is based off this expansion here. So cos of 2nx, consider this nx as sort of the argument, and you're taking cos of 2 times that argument. We know from our double angle expansions that this is cos squared nx minus sine squared nx. Let's just rewrite this such that there's no cos squared. We'll write this as 1 minus sine squared nx. And I think we get cos 2nx equals 1 minus 2 sine squared nx. Rearranging, we get sine squared nx equals a half of 1 minus cos 2nx. This is on your reference sheet, so you don't have to memorize this nor know how to derive this. Okay, but I'm just showing you so you're at least aware where the formula comes from. We can do a similar approach to find an expression for cos squared nx. Okay, we will just be replacing this sine squared with 1 minus cos squared instead of replacing that. And you get this one that's on your reference sheet. Cos squared nx equals a half of 1 plus cos 2nx. Perfect. So now if we can replace this sine squared function with just a normal, with a trig function with a power of 1, we can integrate that as per usual. So let's go back to sine squared. And let's say instead of writing this as the integral of sine squared, if we look at our formula, whatever the argument is, it's equivalent to saying a half of 1 minus cos of 2 times that argument. If this is nx, that's 2nx. Here, it's just 1x. So it would be 2x. Take the half out the front. Should have written this in black. And we get 1 minus cos of 2x dx. Nice. I think we can just integrate this normally because we will leave the half out the front. Integral of 1 is x. And the integral of cos is sine, but because you got to divide by the derivative of the inside, it'll be 1 on 2 sine 2x plus c. And just expanding, we get x on 2 minus a quarter sine 2x plus c. Does that make sense? I mean, there's no response, but I hope that does. Okay, I hope that does make sense. Always replace the square with, you can say a linear trig function, right? Alrighty. Can you have a go using the formula at the bottom of your reference sheet? It's on the bottom of page 2, I believe. Okay, to integrate this. It's pretty easy. So just have a go. Pause and then unpause. Alrighty. So when we do the replacement, this is equivalent to saying a half of 1 plus cos 2x. So I'm just going to take the half out the front and it'll be 1 plus cos of 2x. The integral of this is going to be x plus a half of sine 2x plus c, which is a half of x plus a quarter of sine 2x plus c. Nice. I'm going to give you a few more tricky ones and then, yeah, you can just have a go. So integrate following. Okay, and I'll give you one more for now. I don't know. Oops, let's make this pi on 3. Have a go. I'm now going to go through them. So the first one, if we go to replace that sine squared, it's going to be a half of 1 minus cos of twice the argument, so 6x. Integrating this, it's going to be a half of x minus 1 on 6 sine 6x plus c. And then this is going to be x on 2 minus a 12th of sine 6x plus 6. Perfect. For this next one, that 3 can be taken out. That's sort of irrelevant. Not sort of, it is irrelevant. And then replacing the sine squared with a half of 1 minus cos 2x is going to be that 1 minus cos of twice the argument. So it's going to be 2x minus pi. And then this is from 0 to pi on 2. Dx equals 3 on 2 x minus 1 on 2 sine 2x minus pi from 0 to pi on 2. And I should have given myself a bit more space. So let me take this down. Pi on 2 minus. Okay, let's see. 2 times pi on 2 is pi, minus pi is 0, sine of 0 is 0. So that can sack off. And then if we sub in 0 into this, so minus when we sub in 0, 0 minus, then it's going to be sine of minus pi, which is also 0. So it seems like that's the end of this one. There you go. Alrighty. Let's do the other ones. So this is going to equal a half. Let's write this in blue. A half of, and then the cos goes to 1 plus cos of twice the argument. So 4x plus 2 pi on 3 minus pi on 3 to pi on 3. Whoa, whoa, whoa. Whoa, 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 whoa. What am I doing here? This is abysmal working. Pi on 6 dx. Yep, did I do this correct? Yeah. Then integrating, we're going to get x plus 1 on 4 sine 4x plus 2 pi on 3 from minus pi on 3 to pi on 6. Subbing in, we get pi on 6 plus, and I'm sort of doing this in my head just because I don't want to keep writing out more lines, a quarter sine of 4 times pi on 6 is 2 pi on 3. 2 pi on 3 plus 2 pi on 3 is 4 pi on 3, which is sine of pi on 3 in the third quadrant. So it's going to give you minus root 3 over 2. Minus. And then we're subbing in negative pi on 3. So negative pi on 3 plus a quarter times. So this is going to be negative 4 pi on 3 plus 2 pi on 3. So it's going to give you negative 2 pi on 3. Sine of negative 2 pi on 3 is in the third quadrant, and it's also minus root 3 over 2. Oh, that's worked out really well. Pi on 6 minus root 3 on 8 plus pi on 3 plus root 3 on 8. They cancel. Pi on 6 plus pi on 3 is pi on 2. So it's going to be pi on 4. There you go. And then this last one. So let's do a little bit of a sweep walk so we know not to look there. The negative is irrelevant, so let's just take it out. So this is going to equal negative a half of 0 to pi on 6, 1 plus cos of twice the argument. So it's going to be 2 pi on 3 minus 4x. Yep. Dx. Integrating this, we get x minus 1 on 4 sine of 2 pi minus 4x, 0 to pi on 6. And subbing in, we get pi on 6 there, minus a quarter. Let's see how our mental maths goes with this one. 4 pi on 6 is the same as 2 pi on 3. 2 pi on 3 minus 2 pi on 3 is 0. Sine of 0 is 0. So this goes away. And then when you sub in 0 into that, you get 0 minus And then it's sine of 2 pi on 3, which is root 3 over 2. So it's going to be minus a quarter times root 3 over 2. So minus 1 on 2, pi on 6, plus root 3 on 8. 8. So then this is going to be, I guess we can expand it. So negative pi on 12 minus root 3 over 16. There you go. I hope that helps. That's really as hard as integrating sine squared and cos squared is. Yeah. Okay, and now the only thing I sort of want you to do is have a go at integrating these two. So integrate tan squared x, and then integrate cot squared x. There is no sort of double angle approach for this, but if we use one of our Pythagorean identities, 1 plus tan squared equals sec squared, 1 plus cot squared equals cosec squared, we might be able to replace the tan squared with something that we can integrate. Same thing with the cot squared. Have a go. Pause, unpause. Alrighty. So we can't integrate tan squared directly. So what we're going to do instead is rewrite this as, because we know 1 plus tan squared equals sec squared, we can write this as sec squared x minus 1 dx. This is pretty easy to integrate now, because in the integral of sec squared, we know is 10x. And the integral of minus 1, I guess, is just minus x. So there we go. So that's how you do that one. And then if we go to do this next one, we know that 1 plus cot squared equals cosec squared. So then this can be replaced by the integral of cosec squared minus 1 dx, which is going to give you negative cot x minus x plus c. Very nice, very nice. That really is, I guess, the extent of it. As long as you can sort of recall what to do for these, there's not much else to go to do, except for that little, I guess, reverse chain rule with trig, right? Questions that are actually easier than all of the stuff we've done. So let me just write reverse chain rule. You know, at the beginning, how we said we couldn't integrate sine squared because we didn't have the cos x out the front? Well, now we're going to have the cos x out the front. So it's really applying your reverse chain rule formula. So cos x times, let's make this sine, let's just make this sine squared x. Okay, if we recall our reverse chain rule formula, reverse chain rule, we know the integral of f dash x there you go, that's that. So now you just got to recognize what your function is and what your f dash x is. So it's clear here that the sine x is the function. Do we have the derivative of that function present? I mean, it seems like it. The derivative is cos x. So now we can just straight up apply our reverse chain rule formula and say, well, this is going to be sine x, but not to add 1 to the power. So it's going to be 3 over 3 plus c. Okay. What if you had something like the integral of cos to the 7 2x sine x, or sine 2x? Okay. You need to ensure they have the same argument, or else reverse chain rule doesn't work. You have to do some other approaches. But for us, the arguments are going to be the same. What you're going to say is, what does it seem like my function is? Well, it's the thing that's put to the higher power. It seems like cos 2x is the function, and it's put to the higher power of 7. So f of x equals cos 2x. I need to ensure that in order to apply this rule, I have f dash x present, so the derivative. the derivative of cos 2x is minus 2 sine 2x. So it seems like I'm missing the minus 2, so I'll put a minus a half. And now I feel like we've got it all. We have f dash x, we have fx put to the power of 7. So this is just going to equal minus a half times cos 2x to the power of 8 divided by 8 plus c. So minus 1 on 16 cos to the 8 2x plus c. Okay. I'll give you a few more. Try and recognize what the function is. Try and recognize what, I guess, hence what the f dash x would be or what it would need to be. And then just apply reverse chain rule. Alrighty. So let's, I'll give you a few. Okay, let's do alrighty, have a go. And unpause. So I think we're gonna let here our function be 1 minus cos x. What's the derivative of 1 minus cos x? Well, the 1 goes away, and then you have minus cos x goes to the positive sign. So it seems like this is perfect. This is already put to the power of a half. So we're gonna add 1 to the power. It's gonna be 3 over 2. And then you would divide by 3 over 2. So that's like multiplying by 2 on 3. For this next one, it's more of a general form. So I guess if the function sine x, the derivative is cos x. So you already have f of x to the power of n, and you have some f dash x out the front. So this just goes to sine to the power of n plus 1 x over n plus 1 plus c. Nice. I feel like that should probably be the end of integration using for trig. So yeah, bye.